invited me to such a pleasant place. So my talk will be about exceptional quotient singularities, and it will be based on a joint work with Ivan Chvitsov. So, to start with, recall that the previous speaker advertised the problem of finding Kerenstein metrics on smooth Fano varieties, which is hard and sometimes have a positive answer, sometimes has a negative answer. So let us start with a smooth Fano n-fold. So again, as we know from the previous talk, for it to have a Kerenstein metric, it's sufficient that some particular invariant, and assume that there is a finite group G bar acting on X. Then one may compute some particular invariant of this variety and this group action called alpha invariant introduced by Tian, such that if this invariant is greater than n over n plus 1, then X is Kerenstein. Now, as for a bit more delicate features of Kerenstein metrics, so sometimes there is a way to construct it more or less explicitly. Of course, not explicitly, but more or less explicitly. So assume that you start with some G bar invariant Kerer metric. Starting with this, you can try to solve the equation that there is not, because it's not a metric, it's a form. To solve the equation that the Ricci curvature of some form equals the given form, and fortunately it will always have a solution, and sometimes it will even converge to the desired Kerenstein metric, namely the theorem of Rubinstein. That's somehow analogous to the theorem of Chow. It's just a discrete analog of the theorem of Chow dealing with the Keller-Ricci flow. So the statement is that this converges to the Kerenstein metric, provided that that invariant is greater than 1. So note that greater than 1 means in particular greater than n over n plus 1, so fortunately the metric does exist in this case. And one of the interesting questions about this theorem itself is, do we often have a chance to apply it? So namely, do there exist such varieties that this invariant is large? Actually, they do exist. There are some examples. not many of them fit into large series. So I mean that even the baby version of the question appears to be a bit difficult. So the baby version is the following. Assume that X is Pn. Can it happen that alpha invariant is large? Of course, for some finite group. Of course, it's not very useful because it's not a big deal to find a Kerner-Stein metric on Pn. But still, even in this, even for the simplest possible variety, there is some. It requires some work to build non-trivial examples, and even now we don't know if it can happen for large enough n's. So now, saying said this, let me start the second part of the story, which will converge to this part soon. The second part of the story goes as follows. Assume you have a group acting on a complex vector space. Let it be a subgroup of Gn plus 1 for a while. And consider the singularity, a geom of the singularity, Cn plus 1 over G. For example, if n equals 1 and V is canonical, we have complete classification. Then V is of A, D, or E type. And as everybody knows, this is a series, this is a series, and this is not. So there is definitely something special about E type, and it would be nice to present some explicit property that that makes a distinction between AD on the one hand and E on the other hand. So what is special? E type. And so the partial answer is given by the following definition. So let V be a germ of a chromatolog terminal singularity then V is called exceptional if for any effective Q divisor D, say passing through the point such that the pair is log canonical, there is at most one, and for any log resolution of this guy, there is at most one exceptional divisor with discrepancy -1. So if we restrict ourselves to the quotients of C2 by the final subgroups of SL2, then only the last type will fit into the definition, so it may be considered a more or less direct generalization of this ADE division. So what's good about another special thing about this definition is the following theorem, which is, I guess, due to Prokhorov-Markushevich. Which says that more or less that this happens exactly when this happens. So again, let's so here we must assume that it's reasonable to take a quotient over G, namely that G contains no quasi-reflections. That are elements given by diagonal matrix with 1 and with ones on the diagonal up to the last place and some root of unity in the last place. So assume that we have such a group G, and we take a quotient Cn plus 1 over G, and so it is exceptional if the alpha invariant, let G bar be an image of G in the projective linear group, so that G bar acts on Pn. This happens if and only if. This happens provided that the G bar equivariant alpha invariant of Pn is greater than 1. And the second part is that it is not exceptional if is less than 1. So it's quite possible that this theorem may be stated in a much more neat and nice way. So at least it can be stated in a shorter way, modulo some conjecture. The conjecture is that there exists, so starting from any x and g bar, there exists an effective Q divisor D, numerically equivalent to the canonical class of X, such that the log canonical threshold of D equals the alpha invariant. Sure, yes, G bar invariant equals the alpha invariant of the whole of X. So if you remember the definition from the last talk, alpha invariant is some infimum over all such D's of the values of their log canonical thresholds. And so in all the known examples for finite varieties, for finite groups, one can, and sometimes even for non-finite varieties and non-finite groups, like in the toric case, one can actually find such a Q divisor, so that to compute the alpha invariant, one can one can stop that procedure at some particular stage. But and so the theorem modulo the conjecture says that Cn plus 1 over G is exceptional if and only if the alpha invariant is strictly greater than 1. Okay. So having this theorem in mind, the next task is to I mean that this theorem builds some connection between this and this problem. So describing exceptional singularities is more or less the same as answering the baby version of the question attached to this theorem. So let me pass through some examples.
So,
yeah.
how can you characterize your singularity when the alpha invariant is exactly 1?
How should I do what?
Like,
alpha invariant is 1.
Yeah, so what happens when alpha invariant is 1? So then, so in this setting, it refers to the D type, and it's about semi-exceptional singularities, which I will talk about half an hour later. So let's pass to some examples. And one more remark about this theorem is that it says that the exceptionality of the singularity depends only on the image of G in the projective linear group. So that if you want to replace the canonical singularities, say the canonical singularities here by commutative singularities, which means replace SL by GL, then the only thing we need is to add some more scalars. So to describe exceptional singularities, one may assume that first that everything lies in SL, then because you can always descend to PGL and then ascend back to SL, and then we can also describe everything up to scalars. So So from now on, G will be contained in the cell n plus 1 of C. By the way, this will also solve the problem with quasi-reflection, because there are none in a cell. And an important the next important step is that we have very few possibilities for G to give an exception singularities. Namely, let us say that G is primitive if, so first Cn plus 1 is an irreducible representation of G. And second, there doesn't exist a subgroup in G such that Cn plus 1 splits into a direct sum of equal representations of H so that G permutes VI's transitively. And the classical result from representation theory is that for a fixed dimension, there is only a finite number of primitive subgroups of SL of C, which partially answers the sorry, and there's an additional theorem, is that if our quotient singularity is exceptional, then G is necessarily primitive. So that is a partial answer to the initial question, that this happens not very often. But at least we want to see, but still we want to see an example when it happens. So before stating the examples, let me present some construction which will be responsible for, I guess, more than half of these examples. Namely, let me construct an example of a primitive group. So first start with a Heisenberg group of yes, let P be a prime, and let the group H be generated by, say, X, Y, Z, so that X to the pth power equals Y to the pth power, and so everything equals 1. Z commutes with everything, and X and Y, the commutator of X and Y is Z. So this group has an obvious p-dimensional representation. Namely, we can choose a basis in CP and demand that X shifts the indexes, Y multiplies the eth vector by the root of the primitive root of unity, the pth root of unity, the eth power, and Z does the only thing that it can, namely X by scalar. So this is this representation is irreducible, but not primitive, because you can take a subgroup generated by X and Z, and by Y and Z, and see that it exactly fits into that definition. But now we can enlarge this group a little bit. Then we take the normalizer. So by now we have an embedding of H to SLP of C. Now we can take the normalizer in SLP of C of our group H, and this will be isomorphic to the semi-direct product of H times another finite group, namely SL2 of FP, which acts. So it's a little bit hard to describe the action of SL2 of FP on H, but at least if I take a quotient of H by Z, I get just a two-dimensional affine plane over FP, and SL2 of FP acts there in the most natural way. So this group is usually called the Heisenberg group, and this space is usually called the Weyl representation. And a funny thing is that most of the examples we know will arise from this group. And a small additional construction, this goes for P prime and not equal to 2. A problem with P equal to 2 will be that this group will be abelian for P equal 2, and so that the representation will be reducible, which is not good. So the additional construction for let this p equal 4. It goes as follows. Yeah, you know that in what diameter. So it goes as follows. Take find a group, the quaternion group of 8 elements. So it has a two-dimensional representation. And now take Q8 times Q8 acting on C4, which is C2 times C2. This action is not faithful, but at least the group Q8 times Q8 modular plus minus 1 acts faithfully. So it embeds to SL4 of C. So let it be H4. Now again take let it be H4 with a wave, and H4 will be H4 with a wave generated by this and by the scalar with eyes on the diagonal. And finally, let G4 be the normalizer in SL4 of H4. So now let's return to the desired examples. In dimension 1 there's nothing to do. In dimension 2, all the examples, they're not exactly examples, they're classification in small dimensions. Up to scalars, as usual. And for G in SL n plus 1. So now if n equals 1, then G is one of the E-type groups, which means either double extension of the alternating group on 4 elements, or the double extension of the symmetric group of acting on 4 elements, or the double extension of binary extension of the alternating group acting on 5 elements, and which are E6, E7, E8. Then for n equal 2, this was either known forever or is due to Shakurov. I don't know. N equals 2 is due to Prokhorov and Markushevich. There are more examples, namely G may be isomorphic to PSL2 over the field of 7 elements, which has a faithful three-dimensional representation, or to a triple extension of the alternating group A6, or it is or it arises from this construction, that is H4 is its subgroup, and it is in turn. Sorry, yes, from this construction, sure. H3 is its subgroup, and it in turn is a subgroup of GP. So not all the subgroups fit here, but two of them do. The whole G3 and I guess it's subgroup of index 3 or something like that. And that's all for dimension 2. For dimension 3, namely for n equals 2. Then there comes dimension 3, where the examples are more numerous. First, there are 3 spinor representations of the groups of the double extension of binary extension of A6, binary extension of S6, and binary extension of A7. Then there is a strange group SP4 of F3, which is pretty huge, so it contains something like 25,000 elements, and double extension of this. And 4 more examples arising from that right-hand side construction. Then there's dimension 5, where the life is much easier because 5 is a prime number. Here we have only 2 examples arising from the Heisenberg construction. In particular, if one takes the whole group G5, which has 15,000 elements and is a very famous group due to the fact that it's the automorphic group of the Horrocks-Mumford bundle on P4. Then this gives an example, and one of its subgroups of index 5 also gives an example, and nothing more exists. In dimension, in dimension 6, there are also 2 examples, but of much more irregular nature. Namely, there is a 6-tuple extension of the group A6 acting on C6, and it does give an exceptional singularity. And there is a double extension of some sporadic simple group called the whole Janka group. So it's the sporadic simple group of uh, 604800 elements. It's also a Hurwitz group of genus, some large genus, but this doesn't really matter. So, and finally, the final thing that
Is this group or extension? What is
yes, so this refers to this refers to the simple group, and finally, what the final thing that we know is for dimension 7, and it's really surprising. So in dimension 7 there is nothing. So I would say that it's rather hard to guess any pattern from this bunch of examples, and so possibly one must admit that we don't have a reasonable conjecture about what is going on in arbitrary dimension. Possibly it doesn't depend on what. So up to that nothing, we thought that those should exist in any dimension, and it would be rather easy to construct, but dimension 7 buried all the hooks. So yes, and by now probably it's time to make a step aside and mention one more set of questions related to this. So there's a trivial remark. So assume that G has an invariant or even semi-invariant of degree at most n+1. Then of course the alpha invariant is less or equal than 1, because say if you have an invariant of degree n+1, then it means that already in the anti-canonical linear system you can find a strictly log canonical divisor, which means that with log canonical threshold exactly 1. Or again, at most 1. And when n equals 6?
Yeah, how many?
Many of them. So there are 18 types of them, and some types contain a bunch of. So in particular, for n equals 6, one type consists of the following groups. You can take a group G1 acting on C2, a group G2 acting on C3, and take their product with an obvious action on C2 times C3. And so you can take any primitive group from here, any primitive group from here, and this will give you this will give a primitive group in dimension 6. But fortunately, all this failed to be exceptional just in one move. So I mean that this trivial remark establishes the connection between this bunch of examples and questions to the following old conjecture by Thompson, which says that there exists some constant independent of n such that for any primitive group G in SLN, there is an invariant I guess invariant expected for SLN it may be invariant, but okay, let's be semi-invariant, which means a one-dimensional representation in the corresponding symmetric power. Which means the polynomial acted on by a character of G of degree at most C times n. And this conjecture comes with a partial solution, also by Thomson, which states that at least one can take, instead of a constant times n, one can take 4n squared. And so if one restates the Thomson conjecture in terms of, let it be a weak form of Thomson conjecture. Note that if so again, another part of this to remark is that if we have such an invariant, then the local threshold is at most C. So the weak form of Thomson conjecture is that there is such C that for any group G in G ln LCT of G ln plus 1, the alpha variant of with respect to G bar of Pn is at most C. This is indeed a weak form, because if one has this, he definitely knows this, but not another way around, because the alpha invariant may fail to be large either due to codimension 1 local canonical locus, or to larger codimension local canonical locus. But the fortunate thing is that it goes much shorter and nicer, because here we need not assume that G is primitive. Yes, so here we I guess yes, I guess I believe that here is invariant, not semi-invariant. But yes, so there we really need to assume that G is primitive, because otherwise one can build a series of Schuppen's examples. And here we are free of this assumption, because for non-primitive groups the local threshold is less or equal than 1, so to say, for free. Yes, and the last thing to mention I guess let me say a few words about the situation when we deal with not with strict inequalities, but with non-strict ones. So So this situation also has a special name. This class of singularities is called semi-exceptional singularities, and a better definition is that there exists a unique periodic terminal blow-up. So again, the quotient singularity is like this. If and only if we have a non-strict inequality here, and it's while those singularities we considered before were exceptional also in a philosophical sense, like that, they were sporadic. So there was only a finite number up to some stupid scalars in any dimension. These are not exceptional in that philosophical sense. So then we can, in any dimension, we can present an infinite series of semi-exceptional quotient singularities. For example, take G. Equal some zk to the power n plus 1, and the semi-direct product with either alternating or symmetric group exponent n plus 1 elements. So this is that would be symmetric groups, a symmetric group, so that it is the automorphism group of the Fermat hypersurface of degree k. So then, if k is greater or equal than n plus 1, the corresponding singularity is semi-exceptional. But not exceptional because this group is an imprimitive, so it splits into one-dimensional representation permuted by the permutation group. So and now we can give various values to k so that we have an infinite series of examples in n dimension.
What is the alpha in there?
What?
What is the alpha in there?
One.
Here?
Yeah, that.
One.
I mean,
For this group. For this group. One.
Yeah. So the alpha invariant is exactly 1. So I already told it because I said that it is semi-exceptional but not exceptional. So just to conclude with, after all these experimental considerations, we're left with two interesting questions. So the first question is, can one have alpha g bar of Pn greater or equal than 1 for n large enough, say, I don't know, equal 10. And the second question is that can we have alpha g bar of Pn large enough, also say being greater than 10. And this we cannot answer it. So I guess I will stop here.